Normally, I would just cover this one single section of classifying polynomials and evaluating polynomials. I would call this section 5.3a. I'd wait for 5.3b for a different day, but because we're so far behind and the final's right around the corner, we're going to have to speed it up. So hopefully this all makes sense. Please stop me, even though I'm recording. Please stop me if you have any questions. I can always pause and re-record. So let's begin by looking at this worksheet I just handed out. And this worksheet right here pretty much is about vocabulary, which we should already know. We already know that a polynomial is a simple variable expression with many terms. In order for it to be a polynomial on one variable, it must have only one type of variable, uh, not imaginary, and non-negative exponents. The degree, here's a vocab word we should all get comfortable with. Degree is simply the highest exponent that you see. Okay, so we haven't used it that much in the class, but we're going to start using it. The degree is the highest exponent that you see. So for example, what degree is this polynomial? Anybody? 3, that's right. How many terms does this polynomial have? It has 1, 2, 3, 4 terms. This is out of order because it's not in standard form. Standard form means in order from highest exponent down to smallest. So this is out of order. What would I write to make it in order, which we call standard form? As a matter of fact, before we do that, right here it says standard form. It's another vocab word. Now we've already known standard form when we dealt with parabolas compared to vertex form. Standard form is ax squared plus bx plus c. But the point that we're trying to get here with the vocab definition of standard form, it's a polynomial right here that is in order from highest exponent, power of 2, power of 1, down to the constant at the very end. That's what standard form is, putting in order all of your terms from highest exponent down to smallest. Okay, so this guy right here is not in standard form. How would we rewrite this in standard form? What would my first term be if I wanted to put it in order? Negative x to the third, and then plus 5x squared, and then plus 2x, and then minus 4. Perfect. This is now in standard form. And we kind of already did this with long division and with synthetic division. You want to put it in order before you do long division or synthetic division. Anyway, that's standard form. What else? Leading coefficient. Well, the word coefficient simply means the number that's in front of your variable. So if I said, what is the coefficient of x? The coefficient of x, not x cubed, not x squared, but coefficient of x is positive 2. All right, coefficient is just the number. So all these vocab words should be pretty easy to remember. Constant is simply the number that doesn't change, that doesn't vary. It's the number without a variable. So the constant over here is negative 4. Yay? Okay. So let's go down to right here. These are just how to classify polynomials, first and last name. Usually in the past, I would ask you to memorize this right here. It doesn't matter. It's not on the final exam. So you could use this if on the homework assignments and stuff. You don't have to actually memorize it. But the first name is based on the degree, the highest exponent. So for example, if your highest exponent is 3, the first name would be cubic. If you only have 2 terms, the last name is based on the number of terms. So if there's only 2 terms, that'd be a binomial, right? So again, I'm not going to spend too much time on this, but here's the reality. This guy right here, the degree is 3, so that would make it a cubic and 2 terms binomial. So first and last name of this guy's cubic binomial. Right here, power of 4. If you go up here to the notes, power 4 is quartic. And how many terms does it have? It has 1, 2, 3, 4 terms. So over here, number of terms, 4 or more, it's a polynomial, right? So that would be a quartic polynomial. Anyway, that's just something that you might want to know, but it's not going to be on the final. Okay, what is a function and what is function notation? Well, a function is like g of x, that's just the name of the machine, right? And when I ask you to evaluate a function like find g of 2, what that's asking you to do is to plug in 2 right in there and do the math, right? So plugging in 2 would be x squared plus 1, but notice that when I say x, I put parentheses. Why? Because I'm going to plug in the value of 2 that they want me to plug in. And then you do the math. 4 plus 1, that would be 5. There's your answer. So I hope we remember what a function is. It's just a function notation is having a name right here, and then this is the actual machine. And this notation tells you to plug in that number into the actual machine, right? Any questions on that? All right. Now here it gets a little more interesting when I ask you to plug in an actual variable expression. So if I give you the function g of x equals x squared plus 1, and I tell you plug in 2x in there. So let's show how to plug in 2x. Even though some of us could probably do this in our heads, let's actually show our work here. Again, the g of x function is x squared plus 1. Now, whenever you put a number right here in the parentheses, that's telling you to plug it in. So we plugged in the 2 right in there, right? It used to be an x, it used to be an x. Now there's a 2, now there's a 2. So in this case, you're going to take the g of x function, which is x squared plus 1, and you're going to rewrite it x squared plus 1. And what are we plugging in? 2x. Okay. And we're going to do this math. So what is 2x to the second power? Well, you could use the rule of exponents that if you have a monomial in here, you distribute the outside exponent to the inside, or you could just think, what is 2x times itself, right? What is 2x times 2x? That's 4x squared. Bring down the plus 1 and you're done. This is your answer. Cool. Now, there will be, I believe, at least one of these types of questions on the final exam. So I hope we understand this. It's not difficult. I mean, it could get difficult, right? I could ask you to plug in g of x plus 3 on that same function, g of x. Let's do that one, okay? So we're going to use the same function, g of x, and we're going to plug in g of x plus 3. So what does that mean? G of x is really x squared plus 1. And again, start with parentheses. X squared plus 1. So we're going to plug in this binomial this time, x plus 3. It does get a little more challenging, but it's all just algebra 1 stuff. When you plug in the x plus 3, obviously you're going to do exponents first and then add 1 at the very end. So we're going to do x plus 3 times x plus 3 and then plus 1 at the very end. And of course, when you multiply a binomial with another binomial, you have to do distributive property and combining like terms afterwards. X times x, x squared, x times 3, 3x. And then 3 times x is another 3x, and 3 times 3 is 9. And of course, you bring down that 1, and then you combine like terms. Well, you could combine the middle term 3x with the middle term 3x, and that'll give you a positive 6x. Then, of course, you bring down that x squared. And what about the 9 plus 1? You could combine those, and that'll be a 10. And there's your final answer. It's a quadratic trinomial. So g of x plus 3, the answer is x squared plus 6x plus 10. So normally I would spend more time on this. How do you guys feel about it? Should we do one more or just move on? Okay, for the sake of time, we're going to move on. Backside of your notes, you do have this worksheet here. And it's practice, but then again, because of the sake of time, I'm not going to ask you to do every single question. But we understand how to do this, right? Like, for example, down here, you have P of X is this and R of X is this. This is the machine that's called P of X. This is the machine that's called R of X. Right here, they're telling you use P of X and plug in 8A right in there. So you're going to go A squared. That'll be a 64A squared. Multiply it by 3. Put the minus 4 at the end. That's your answer, right? You guys could practice this and check your answers on Google Classroom, and that'd be good practice. You know what? On this top section, it might be worth reminding you guys that synthetic division that we learned just recently also could be used as synthetic substitution. For example, number 8, you could plug in, like right here, it says plug in P of negative 2. So one option is to write 3 to the third, x to the third minus x to the second plus 2x minus 5. So one option is to actually plug in the -2 right in there. -2, -2, -2. And you could do all this math. You could even do it with the calculator and get an answer, right? And that answer would be the answer to p of -2. But you could use synthetic substitution, synthetic division, but as substitution, like you could actually directly plug in that value -2. So if you went for synthetic substitution, you could plug in the -2 and then make a list of your coefficients when it's in standard form, which it is, representing every power, even the missing ones, which there is no missing powers, power 3, power 2, power of 1, and constant. So you're going to put 3, -1, 2, and -5. 3, -1, 2, and -5. And as you go down, you combine. 3 plus nothing is 3. As you go up, you multiply. -2 times 3 is -6. As you go down, you combine. -1 minus 6 is -7. As you go up, multiply. -2 times -7 is +14. As you go down, combine. 2 plus 14 is 16. As you go up, multiply. -2 times 16 is -32. As you go down, combine, you're going to get -37. Normally, we call this a remainder, right? But if you're using synthetic as substitution, not division, then it's not a polynomial answer with the remainder over the original divisor. It's actually the answer to plugging in -2. So when you plug in -2, you're going to get out a -37. If you were to go over here and go -2 to the third, that's -8 times 3 is -24. Right here, -2 squared is 4 with the minus sign in front, so -4. -2 times +2 is -4. Add all those, you're going to end up with -37, believe it or not. Okay, so that's just something interesting that you could use synthetic instead of division. You could use it as substitution. You don't think opposite on what you plug in. You just plug in the value that they want you to plug in into synthetic substitution. And instead of the remainder, that gives you your output. Input -2 gives you your output -37. And it's funny that I just mentioned inputs and outputs because what are inputs and outputs? Inputs and outputs are actual coordinates, right? Inputs and outputs are x and y values on a coordinate plane. So believe it or not, if I wanted to, I could take this equation, uh, p of x being 3x to the third minus x squared plus 2x minus 5. I could plug in the number 1 and get out an output. And that'll be a coordinate on the plane, on the xy plane. I could plug in a 2, get an output. I could plug in a 3, get an output. I could plug in a -2, get an output. These are all coordinates on an xy plane. And the next part of this lesson that I would normally do on a separate day is talking about graphs and their end behaviors. Okay. So, what I would like you to do right now um, is go to desmos.com on your Chromebooks, and I want you to type in some odd degree functions. Right now, I want you to type in like y equals x to the third, y equals x to the fifth, y equals x to the seventh. Go to desmos.com and type in any odd degree function you want. Even the first one, y equals x, like that's an odd degree function. The power is 1. I want you to graph those, and then in a couple of moments, we'll look at them on Desmos, and let's conclude whatever we see, or let's make a conclusion of what we see. So if you're at desmos.com and you type in y equals x and then hit enter, and then it'll go to the next one, and you could graph all of these on the same xy plane, so we could just visually see them all together. Okay, so here it is. Um, on Desmos, we have y equals x, which is that straight line. That's algebra 1 stuff, right? Y equals mx plus b. It crosses the y-axis at 0, and the slope is 1 over 1, up 1 over 1, up 1 over 1. There's your line diagonal, perfectly straight. But what happens when we put an odd degree of 3, and then 5, and then 7? We end up with a similar type of graph. It's like a squiggly line, right? Squiggly line, right? Um, but what could we say about all of these odd degree functions? Anybody? What do you notice? All of them end up in quadrant 3 and in quadrant 1. Yeah? Like, and this makes, I mean, just go off the first one, y equals x. Yeah, it starts down here from left to right. It's going up, 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 all the way that way. right? So any odd degree function is going to have an end behavior. I'm introducing this vocab word right now, end behavior of down here and up here. End behavior. Now, what do I mean by end behavior? How does it end up? So as you go to the left, where does it end up? It ends up way down here, right? As you go to the right on the x, so where do you end up? You end up way up here, right? Um, and I might as well introduce this right now. How would we actually write this? As you look to the left, it ends up, as you look to the left, it ends up down here. Mathematically, this is what you would write as x approaches negative infinity. That means as you look to the left, okay? I would write this down if I were you guys. As x approaches negative infinity, then your y values, but as x goes to the left, to the negative infinity, where are your y values going? To positive infinity or negative infinity? Negative infinity, right? So we're going to say as x approaches negative infinity, and most books don't say y approaches negative infinity. Most books say uh, f of x, which is the same thing as y, approaches negative infinity. So what this is saying, this notation right here, what it's saying is as you look to the left, it's going down forever. As your x values get negative, your y values also get negative. That's what it says. As your x values get negative, your y values also get negative. And that describes how the graph ends up, okay? All of these graphs that have an odd degree function, power of 1, power 3, power 5, power 7, you could do, bless you, you could do y equals x to the power 13. It's going to end up down here and up there. And this is how we mathematically state that fact. The end behavior is as x approaches negative infinity, f of x approaches negative infinity. Um, what if I were to write this down as x approaches positive infinity? What do my y's do? Approach positive infinity. And ladies and gentlemen, this is a lesson in itself. Uh, describing end behavior. Describing end behavior. Now, I'll be honest with you. Um, if you put anything else on this x to the third, like if you were to put y equals x to the third plus 2x squared minus 1x plus 17, some other crazier things might happen in the middle, but the end behavior will always be the same. It'll always end up down here and up there. Does that make sense? If I take any function like y equals x to the seventh, and if I do like plus 2x to the fifth minus 4x to the third plus 1x, take away 7, um, something else is going to happen in the middle. There's going to be some funkiness going on, maybe some ups and downs, but the end behavior will always be down here and up there. And this is how we describe that end behavior with the appropriate mathematical notation. As your x values go to the left, your y values go to the bottom. As your x values go to the right, your y values go up. Make sense? Okay. Now, I want you to go and, but how about this? Before doing this in Desmos, I want you to put a negative sign as your a value on all of these. What do you think is going to happen if I put an a value of -1? If I put a negative sign in front of all of them? You guys remember a value before, right? What would happen if your a value were negative? It would get, the transformation is that it would get reflected over the x-axis, okay? So if I were to take these guys and if I were to put the a value of -1 instead of 1, what do you guys predict is going to happen to all these graphs? If I put a negative in front of all of them, what's going to happen? It's going to switch. It's going to reflect over the x-axis. Now, what does that mean? These guys that were down here and these guys that were up here, when you reflect over the x-axis, it flips the whole thing. Yay? So if you do that right now, go ahead and put a negative in front of the x, a negative in front of the x cubed, negative in front of the x to the fifth, and you will see this right here. It gets reflected. It gets reflected over the x-axis. Make sense? Okay. So if your a value is negative, on an odd degree function, if your a value is negative on an odd degree function, how could we describe the end behavior? Well, we're going to say as x approaches, let's always start by describing what happens to the left. As x approaches negative infinity, f of x, the y values approach what? Positive infinity. And this is on the final, guys, right here. This notation's on the final exam. And then he would say, as x approaches positive infinity, then f of x, whoa, that's ugly. Then f of x approaches what? Negative infinity. Okay, I'm hearing a lot of you saying it, but I need everybody to understand it, right? As x approaches, as you go to the left, as x goes to the negative, here's your x-axis, going to the negative, where are your y values going? They're going up here. So as your x get negative, your y's get positive. As your x get positive, your y's get negative. Make sense? Okay. And again, this is end behavior. And, well, end, that's ugly, end behavior. Okay. Now, something else could happen right here in the middle, right? Like if we look at, um, let's say this guy right here. Or no, not that guy. Let's go for the biggest one right here, this guy. And if you were to change that to like a negative x to the seventh plus x to the fifth, take away 2x to the fourth minus x squared plus 7, then when you graph that, something else may happen right here, but it's still going to end up going this way forever and that way forever. But something else may happen right here, some other type of squiggles. Does that make sense? Okay. Anyway, how about we graph some even degree functions? Okay. So even before graphing these, we already know what y equals x squared looks like. What does that look like? What is y equals x squared? It's the parent graph of what? Parabolas. It's a U-shaped curve. It's opening up. So based on your observations of the previous odd degree functions, what do you think is going to happen with these even degree functions? They're all going to open up. That's right. Go ahead and type them in. Check them out. When you type them in, you're going to see a bunch of parabolas in a sense, not regular parabolas, but some type of U, right? But the reality is, this is strictly, these notes right here are strictly on end behavior, okay? So when when you have an even degree function, they're always going to end up here, the end behavior. And let's describe that end behavior. The end behavior of all of these is as x approaches negative infinity, f of x approaches what? Come on, guys. Is it positive or negative infinity? Positive. As x approaches positive infinity, f of x approaches what? Positive infinity. Okay? As x goes negative, here's 0 on the x. As you go -1, where are you going on the y? Up. As you go -2, where are you going on the y? Up, right? So as x goes negative, the y's go positive. As x go positive, the y's go positive. As x goes positive, the y goes positive. As x goes positive, the y goes positive, right? But again, this is a notation we need to get comfortable with. As x approaches negative infinity, the y values, the f of x approaches positive infinity. As x approaches positive infinity, f of x also approaches positive infinity. Now, what would happen if I put an a value of -1 in front of all of these? What would happen? It's reflecting over the x-axis. So this is what would happen. Let me show you. It just reflects over the x-axis. So what would the end behavior right here be? You would say as x approaches negative infinity, f of x approaches what? Negative infinity. As x approaches positive infinity, then f of x approaches what? Negative infinity as well. Okay. Are we getting comfortable with the notation and with the concept? I hope. As x approaches negative infinity, as you go to the negatives on the x, where does your y go? It goes down here in the negatives. So as x goes to negative infinity, y's go to negative infinity. And just a different name for y is f of x. As x goes to positive infinity, where are your y's at? Also negative infinity. Okay. So what could we conclude here out of what we've been observing? Um, any even degree function, let me start right here. Any even degree function, any even degree function is going to have an even amount of arrows either opening up or down as their end behavior. Okay. Uh, end behavior will be both up if the A value is positive or both down. That's the end behavior. Like, I don't know what's happening in the middle, but I know how it ends up. As you go to the left, it's going to go up. If the A value is positive, as you go to the right, it's going to go up, right? And that makes sense because we know the easiest, most basic type of uh, even degree function, which is a parabola. And how does a parabola end up? It ends up there and up there, right? Or negative, it would end up down here and down here. But the reality is, any even degree function is going to end up both up here or both down there. Okay, you're going to have an even, you're going to have both arrows up or both arrows down. And we could also conclude that any odd degree function, and if you look at the most basic odd degree function, would be a line, right? Where does that end up? It ends up down here and up here if your A value is positive. But if your A value is negative, it would flip and end up here and down here. Does that make sense? Más o menos? Is it too much? Yes, it is too much, or yes, you understand? All right. How about this? So this is a great page of notes. And I know you guys are like, what the heck? You're giving me too much. Um, this is what we would normally do on a second day, but and if you wanted to see the whole thing, I would go to Google Classroom and see my previous videos. But the reality, this would be great practice for you to evaluate. Like, here's your f of x function, and they tell you state the leading coefficient, that'd be a -3. State the degree, that'd be the power of 3. State the constant, that'd be -1. Classify it, or that'd be a cubic trinomial if you put it in order, right? And then they tell you, like, find g of c minus 1, take away 3g of 2c. But I'm not going to do that right now because we're running out of time and it's already been too long of a lesson. Right now, I want to continue with the concept of end behavior. Okay. So we already talked about end behavior, and here's just a reiteration on these notes. If your polynomial function has an even degree function, then the end behavior will be in the same direction. X to the second, x to the fourth, x to the sixth, all open up. We already did that on Desmos. Likewise, y to the -2, y equals x to the -2, y equals x to the -4, y equals x to the -6, they all open down. We already saw that on Desmos. If your polynomial function has an odd degree function, then it's going to end up in quadrant 3 and quadrant 1. Okay. How about this? A lot of us are confused of what y equals x to the third looks like. This will help you understand what x to the third looks like. I mean, of course, you could draw it on Desmos, but what is a function after all? It's just a collection of its solutions, and you could find the solutions with the xy table. So when you plug in, let's say -2 or -3, if you plug in a -3, no, not -3, -2, 2 would be better. So let's plug in a -2. What is -2 to the third power? That's -2 times -2, which is +4 times -2, which takes you back to a -8. What is -1 to the third power? -1 times -1 is +1 times -1 is -1. What's 0 to the third power? 0 times 0 times 0 is 0. How about 1 times 1 times 1? That's 1. How about 2 times 2 times 2? That's 8. And these are all coordinates. That's a point, that's a coordinate, that's a coordinate, that's a coordinate, that's a coordinate. So just a quick sketch on an XY plane, 0, 0 is right there. And then you have -1, -1, -1, -1, that would be right there. And you have -2, -8, that'd be way down here somewhere. And then if you go to 1, 1, that would be here. 2, 8 would be up here somewhere. So you do end up with this squiggly line, snake-like curve, crosses right there, then it curves up. And we already saw that on Desmos. But all of these cubic functions, anything to the third power, is going to have some type of like snake-like curve. All right. But if your A value is negative, of course, it gets reflected over the x-axis. So your end behavior would be like this. Instead of up here and down here, it's going to be up here and down here. Okay, so if they ask you to find the real zeros, the real zeros, what the heck are real zeros? Anybody? It's on the wall right there. Real zeros are simply answers. They're simply solutions. They are x-intercepts, right? Roots are the same thing as answers. Zeros are the same thing as answers. But the word real, it does mean something. Real means an actual real number, okay? Like an actual real x-intercept. What do you mean, or what do I mean by real as opposed to not real? I'm talking about there are some answers to polynomial functions or equations that are imaginary, right? We've dealt with the I before, okay? But when I say real answers, I'm talking about real um, x-intercepts, like you could actually see it when you graph it. Okay, so hopefully you guys could pay attention to this last part of the lesson. This guy right here, I could tell you right now, or you could tell me, is it an odd degree function or an even degree function? It's odd. It's odd. Why? Because we know end behavior. If this arrow were down here and this arrow were down here as well, if they were both opening down, then that would be an even degree function. If they were both opening up, it'd be an even degree function. But if one opens down and one opens up, that's an odd degree function, right? Okay, now let's teach you a little bit more. Um, could this be the power of 3? The answer is no. You don't know yet because I haven't taught you this yet. Okay. But the direction in which the graph is going actually tells you the minimum degree it has to be. Okay. I'm sorry. This is so important. And for the last part of this long, long lesson. If you've been falling asleep right now, wake up. If I look at the direction, so like right here, going from left to right, I'm going in one direction, and then 2, and then 3, and then 4, and then 5. That means that this function, I don't know the function, but this function, what I do know about it, it has to be at least the power of 5. Okay. And I also know that the A value has to be positive because anything with the A value of positive, odd degree function, and behavior is down here and up here. But the directions, the number of directions has to be that that'll be the least your degree could be. Okay. So this cannot be the power of 3. It has to be at least 5. It could be 7, could be 15, could be 91, but it has to be at least the power of 5. It cannot be the power of 3. Okay. Um, this guy right here, is it a odd degree function or even degree function? Even. Okay. Now, could it be y to the second power? No, y to the second power makes a parabola, right? It's just a regular U-shaped curve. What does this have to at least be? What's the lowest possible degree that this function could have? Exactly. One direction, 2 directions, 3 directions, 4 directions. So it at least has to be y equals x to the 4th. Now, of course, some funkiness happens right here. So it's not just y equals x to the 4th. It's probably gonna be like y equals x to the 4th minus 3x to the 3rd plus 2x squared, something like that, right? So, but anyway, this does tell us that it has to be at least the power of 4. Does it have to be 4? No, it could be 6, could be 8, could be any other higher even degree function. Okay. Um, what else? Since we're on these graphs, you guys remember maximum and minimum, right? The maximum value is the highest value it gets to. What is the maximum value of this guy? Will it get to 1? Will it get to 1? Will it get to 2? Yes. 3, 4, 5, 1,000, a million? Yes. Why? Because the arrows go up forever. So there is no maximum, like absolute maximum. Like the maximum is just positive infinity, right? What is the minimum value here? About negative 1, 2, 3, right? That's the minimum value. Okay. Okay. So those are also things that we're going to have to understand before the final. How about this guy right here? Um, is there a maximum? No. Is there a minimum? No, because the maximum it goes up forever, the minimum it goes down forever. Okay. Now let's throw in some new vocab words, and you might want to jot this down. Um, this guy right here is a relative max value. Relative max value. It's not the absolute max value, but it's the relative max value. In other words, if you zoom in, just to that piece right there, just from here to there, is there a maximum? Yeah, that's one little maximum. That's what we call a relative maximum. Okay, a relative maximum. Here's another relative maximum. Relative max. Because if you just look at this part right here, from here to here, that's the highest point. That's the relative maximum. It's kind of like saying, uh, who's relatively the tallest person right here in this class? It could be, I mean, it's going to be one of us, but are we the tallest person in the world? Heck no, right? But relative to this classroom, you could have the maximum height. But compared to the rest of the world, you're not the absolute highest person, right? It's just a relative max height. Okay, now some of them, like down here, these guys, these are absolute minimums, right? It looks like maybe this one comes down a little bit further. So you could say it is an absolute minimum. I mean, if they were both the same, then both of them would be absolute minimum. Let's look at a different one. All right. Is there an absolute maximum on this one? Yes. Where's the absolute maximum? What x value is the absolute maximum? At what x value? You said it? Somebody said it? Negative 2. So if you go to the x value negative 2, boom, that's your highest point right there. This is what we call absolute max. Now, what would we call this maximum value? We can't call it absolute. Yeah, you call it relative. Relative max value. Okay. Is there an absolute minimum value on this graph? No. Is there a relative minimum value on this graph? Yes. What x value would produce the relative minimum? Yeah, the x value of 1 would produce this relative min. Does that make sense? All right, great. We're definitely learning this stuff. That's awesome. Now, let's go back to the degree. If I wanted to know what the highest power must be, the degree of this has to be at least what? 4. Okay. So what could we tell about this graph? We know it's going to be y equals or f of x equals. We also know that the a value is going to be negative, right? And we know that it's going to have x to the 4th at least. Could be x to the 6th. Could be x to the 8th, but at least x to the 4th. It cannot be x squared. How about that puppy right there? Look at that. Uh, y equals, is the a value going to be positive or negative? It's going to be positive. Okay. So y equals, and we're going to have some type of x. And what's the degree of this one? At the very least, it has to be 6. Let's see. 1 direction, 2 directions, 3 directions, 4 directions, 5 directions, 6 directions. At the very least, it's going to be an x to the 6th. Yes. Now, of course, you're going to have some other stuff because other stuff happens. The end behavior is up here. End behavior as x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches positive infinity. Okay, dang. I'm sorry. This is like 3 days worth of lessons in one period, but I hope it makes sense. Okay. Do we have a Actually, let me just ask you, at what x value do I have an absolute minimum value? At the x value of 1. The x value of 1, you have an absolute minimum. This would be a relative. This would be a relative. And we don't have an absolute max, but we do have two relative max. Okay. All right, guys. I apologize for the long lesson. I'm done. What is good question? Sorry, one more last detail. What is the difference between a relative max compared to an absolute max, or a relative min compared to an absolute min? Like this graph right here, is there an absolute max, like the highest in the whole world, right? Is there a highest point in the whole world? No, because it keeps going up forever, right? Is there a absolute minimum value in this graph? Yes, there is this is the lowest it goes. Nowhere else is it going to go lower. Nowhere else is it going to go lower. This is an absolute, but this guy right here is a relative min, right? So what's the difference between a relative min and a absolute min? Well, this guy right here, if you just look at that, it looks like a parabola. That's a minimum value, but is it the absolute lowest point? No, it's not. So that's what we call a relative, right? It's relative to this area. That minimum value is relative to this area. But if you look at the bigger picture, there's other points that are lower than this one. This is the absolute minimum. So that's the difference between relative minimum and absolute minimum. Okay? And the minimum value doesn't necessarily have to be below the x-axis, right? You could have, like, let me just draw it up here. You could have like this, right? Well, where's the relative minimum? Relative's right here. Where's the absolute minimum? Right here, right? Is there an absolute max? No, because it goes up forever in both directions. Is there a relative max? Yeah, that'd be this guy right here, right? Okay. By the way, this would have to be an even degree function, and it would have to be at least 1, 2, 3, 4, right? 4 degree polynomial.